Hello, and welcome to Solutions for Problems out of Section 8.1. So we begin with this problem, number 11. We're given a right triangle. Note the square mark in the bottom right corner of the triangle indicating a right angle. We are given the length of the right side A, this is 10, the bottom leg B, this is 7 units long, and we're asked to find each of the 6 trigonometric functions of this angle theta in the upper corner. So those 6 functions will be the sine of theta, the cosine of theta, the tangent of theta, these are the 3 primary ones, but then we also need to find the cosecant of theta, the secant of theta, and the cotangent of theta. Here are our 6 basic trigonometric functions. Okay. Now, since we are given A and B in a right triangle, we can use, I'm just going to draw a larger copy of the triangle over here. So here is our angle theta. We have the side length 10 and we have this length 7. Okay, so first, let's find the length of this hypotenuse. Now, since we are in a right triangle, we can use the Pythagorean theorem. The sum of the 2 legs squared is equal to the length of the hypotenuse squared. Okay, so 7 squared is 49, 10 squared is 100, so we have 149 is equal to h squared. So h is equal to the positive square root of 149. Okay, now often if you were working purely algebraically, you would need to do h as plus or minus the square root of 149, but since we are dealing with the leg of a triangle, it does have a positive length. Okay, so with that work behind us, I'm going to label this side as being of length square root 149. And then I'm going to erase all of this work here just to clear out some space. Okay, with any 2 side lengths in a right triangle given, you can find the third with the Pythagorean theorem. So now the sine of an angle in a right triangle will be given by the ratio of the opposite side length divided by the hypotenuse. The side opposite the angle theta is of length 7, and the hypotenuse is of length square root 149. Well, as soon as we have the sine, which I'm going to go ahead and put over here, 7 over root 149, we immediately get the cosecant of theta, because this is just 1 over the sine of theta, or it's the hypotenuse length over the opposite length, but it's just the reciprocal of sine, so instead of 7 over root 149, it will just be the square root of 149 over 7. So I'll go ahead and label this down here for my cosecant, 149 over 7. I'm just going to clean up this mark. That 4 looks a bit too much like a 9. Okay, so we have the square root of 149 over 7. And we found our sine and our cosecant. Sine and cosecant sort of go together nicely like that. So next, let's move on to the cosine. So rather than being the opposite side length over the hypotenuse, okay, so we find our cosine of an angle by taking the adjacent side length over the hypotenuse. The adjacent side to this angle theta is of length 10. The hypotenuse is still of length root 149, so there is our cosine. It is 10 over the square root of 149. As soon as we have our cosine, we can take our secant by just doing 1 over the cosine of theta, provided that wasn't 0, and in this case it isn't. That's just going to be the length of the hypotenuse divided by the adjacent side, but it's just the reciprocal of cosine, so it's the square root of 149 over 10. So that is our secant, root 149 over 10. And finally, with our sine, cosine, cosecant, and secant done, we can move on to our tangent. We have a few options here. For example, the tangent of an angle can always be found by taking the sine of the angle divided by the cosine. And since we have sine and cosine, we could do that. But since we also have all of the sides labeled in a triangle here, it's going to be a bit faster just to go ahead and do that. So we're going to go ahead and say the tangent of theta is the opposite side length over the adjacent side length, or 7 over 10. And the cotangent of theta is the adjacent side length over the opposite side length, which is just 10 over 7. This is also 1 over the tangent. And there we have it, all 6 trigonometric angles given. Depending on a personal preference or instructor preference, Some people take issue with leaving radicals down in the denominator, for example, here in the sine and here in the cosine. And if you want, you can go ahead and clean these up, both of which I simply multiply by root 149 over root 149. So this could be called 7 times the square root of 149 over 149. And this would just be 10 times the square root of 149 over 149. Note, as numbers, they are already the same thing. It's just a matter of what's required. Some entry systems require no radicals in the denominator, for example. All right, moving on to the next problem. Very similar, we're given a right triangle with 2 side lengths given, and we are asked to find all trigonometric functions of the angle. However, the unknown side length is not the hypotenuse. So if I call this side length x, the Pythagorean theorem will tell us that the sum of the 2 sides squared is equal to the length of the hypotenuse squared. So this gives me 1 plus x squared equals 5. Subtracting 1 from both sides yields x squared equals 4. X is plus or minus 2, but since it is a side length, we need x equals 2. So as before, I'm simply going to label that side length and erase all of the work that accompanied it. So this side length is definitely of length 2. And now we can go right on to finding all 6 trigonometric functions of the angle theta. And again, the trigonometric functions that we're looking to find are the sine of theta, the cosine of theta, the tangent of theta. Once we have those 3, it's pretty quick work to go ahead and get the cosecant of theta, the secant of theta, and the cotangent of theta. So the sine of theta is opposite side over hypotenuse. The cosine is adjacent side over hypotenuse. The tangent is the opposite side over the adjacent side. The cosecant is 1 over the sine, which is just the hypotenuse over the opposite side. The secant is 1 over the cosine, which will be the hypotenuse length over the adjacent side. And the cotangent is 1 over tangent, which will be the adjacent side length over the opposite side. And we simply have to be careful about what counts as opposite versus adjacent versus hypotenuse. Well, the hypotenuse is root 5. The adjacent side to the angle theta is 2, and the opposite side to the angle theta is 1. So now I can simply go and fill all of this in. Okay. So the sine is opposite over hypotenuse, or 1 over root 5. If leaving radicals in the denominator is not desired, you can call this root 5 over 5. That's multiplying top and bottom, numerator and denominator, by root 5. Cosine is adjacent to over hypotenuse root 5, and again, if it's necessary to clear out radicals from denominators, you can multiply by root 5 over 5 to get to root 5 over 5. Tangent is opposite 1 over adjacent 2, 1/2. Cosecant is hypotenuse root 5 over opposite 1, so just root 5. Secant is hypotenuse root 5 over adjacent 2, so just root 5 over 2. And cotangent is adjacent 2 over opposite 1, which we can simplify just as 2. And there you have it, very similar to the last problem. Really, the only difference is that the missing side was not the hypotenuse, it was something else. Okay, let's move on. Problem 31 is very similar, but it's now phrased slightly differently because we are given a triangle where nothing is labeled, except then we're given this textual information. A is equal to 9, so I'm going to go ahead and label that here. This angle is 10 degrees, and we are asked to find everything that is not labeled. Okay. Now, we do have 2 angles in the triangle, which means finding the third is pretty straightforward. So, A plus B plus the third angle, which is 90 degrees, must equal all angles of a triangle add up to 180 degrees. Now, if this were measured in radians, we would say A plus B plus pi over 2 is equal to pi. Remember, 90 degrees is pi over 2, and 180 degrees is pi radians. But since B was given to us as a degree measurement, we'll keep everything in degrees. And specifically, B was given to us as 10 degrees. So let's plug that in. If I subtract 10 and subtract 90 from both sides, we're going to end up with A is equal to 80 degrees. So there's our missing angle, which I'll put up here. Okay. I'll also label it in the triangle in case we need it later on. And now we can go on to finding our missing side lengths. Now I could try using the Pythagorean theorem. If I use the Pythagorean theorem, I would say the sum of the two legs, which is 9 squared and b squared, must be the hypotenuse squared. But notice I have two unknowns here, both b and c. So this is not terribly helpful at the moment. If I could find one of them, however, I could use it to find the other. We're going to have to make use of some trigonometry. For example, notice that 9 is opposite from the 80-degree angle, but it's also adjacent to the 10-degree angle. Okay, looking up in the upper right corner where this triangle is drawn, the side length of 9 is adjacent to 10 degrees, but it is opposite from 80 degrees. And therefore we've got some options. Okay. So if I was to use the fact that 9 was opposite from 80 degrees, I could say that the sine of 80 degrees is opposite over hypotenuse. Opposite from 80 degrees was of length 9, and the hypotenuse of this triangle is c. So notice that we now have the sine of 80 degrees is 9 over c. If I cross multiply, we get c times the sine of 80 degrees is equal to 9. I can now divide by the sine of 80 degrees and say c is equal to 9 over the sine of 80 degrees. You could alternately call this, since you have division by the sine of 80 degrees, you could call this 9 times the cosecant of 80 degrees. But honestly, it would be more common just to leave the sign in the denominator. We could have also said that 9 is adjacent to 10 degrees. So we could have said that the cosine of 10 degrees is equal to the adjacent side over the hypotenuse. Adjacent to 10 degrees is the length of 9, and the hypotenuse is still c. So I have that the cosine of 10 degrees is equal to 9 over c. Notice if I compare cosine of 10 degrees equals 9 over c, sine of 80 degrees equals 9 over c, what we find is that the cosine of 10 degrees is equal to the sine of 80 degrees. This is where the term cosine comes from. The cosine of an angle is the sine of the complementary angle. Okay, so we could have solved it this way. Instead of ending up with 9 over the sine of 80 degrees, we could have had 9 over the cosine of 10 degrees. Both answers would be perfectly correct. Okay, so that is our hypotenuse c, so I'll go ahead and write that up here. I'm just using cosecant, so I don't have to write a fraction. It really doesn't matter. We still, however, need to find the side length b. As is convention, side lengths are lowercase letters and angles are capital letters. Observe that the side length letter is across from the angle letter. So across from angle capital B is side length lowercase b, and across from angle capital A is side length lowercase a. Now in order to get the side length b involved in a trigonometric ratio, I need to see how it relates to the two angles that are given. It is opposite from 10 degrees, or it is adjacent to 80 degrees. Now what I can do is I could say something like, great, so therefore the sine of 80 degrees will be, sorry, let me do the sine of 10 degrees, apologies. The sine of 10 degrees will be the opposite side divided by the hypotenuse. Opposite from 10 degrees was b, and the hypotenuse is c. But I have already found c. It's 9 times the cosecant of 80 degrees. So now I have the sine of 10 degrees is equal to b over 9 times the cosecant of 80 degrees. Division by the cosecant of 80 degrees is just multiplication by the sine of 80 degrees. Now if I cross multiply, we get 9 times the sine of 10 degrees is equal to b times the sine of 80 degrees. And now I can divide by the sine of 80 degrees and get that b is 9 times the sine of 10 degrees divided by the sine of 80 degrees. This is a perfectly legitimate way to do this problem, but it's not the only way. Okay. We could have also used the fact that it is adjacent to 80 degrees to end up with a cosine of 80 degrees, similar to how we found c in a couple different ways. Okay. However, we could also say something like, notice, b is our unknown side, but a is a nice straightforward number. It's just 9. So if we can set up a trigonometric ratio that uses a instead of c, the numbers might look a little nicer. And if I want to use the two legs of a triangle and not use the hypotenuse, I'm talking about either a tangent or a cotangent. So if I set up, for example, that the tangent of 10 degrees, well, that's going to be opposite over adjacent. Which side is opposite the 10-degree angle is b, which side is adjacent is a, which is of length 9. And now if I cross multiply, we simply get b is equal to 9 times the tangent of 10 degrees. Okay, this is quite correct. Okay, if I look back at our prior work, we've already observed that the sine of 80 degrees is in fact the cosine of the complementary angle, and complementary to 80 degrees is 10 degrees. And now we have sine of 10 degrees over cosine of 10 degrees, which is the tangent of 10 degrees. It's the same answer, whichever way you did it. Okay, moving on. Just like the last one, we are given a few things in a right triangle. We are given this upper angle is 15 degrees. And we are given that this bottom side is of length 3. And now let's find all of the other sides and angles. Well, again, the missing angle is most straightforward. If I add the 3 angles up, the unknown b, the given 15 and given 90, I should end up with 180 degrees. Subtracting 105 degrees from both sides gives that b is 75 degrees. Okay, so b is 75 degrees. That's quite straightforward. Now what we have to do to find our missing side lengths of b and c are set up some trigonometric ratios. Now what I could do, for example, is I could set up the sine of 75 degrees. I could say, great, the sine of 75 degrees is opposite over hypotenuse. Well, which side is opposite 75 degrees, this angle b? Side length b. What is the hypotenuse? C. But I don't know either of those, so this is not very helpful at this point. Try to set up a trigonometric ratio that only has one unknown in it. And since I don't know either b or c, I don't want to set up a trigonometric ratio that uses both of them. Okay, so instead of using the sine of 75 degrees, I could, for example, use the cosine of 75 degrees. If I use the cosine of 75 degrees, that will be the adjacent side over hypotenuse. The side adjacent to 75 degrees was of length 3. So I have the cosine of 75 degrees is equal to 3 over c. And if I cross multiply, c times the cosine of 75 degrees equals 3, or c is equal to 3 divided by the cosine of 75 degrees. If you prefer, you can call this 3 times the secant of 75 degrees. Okay, so there is our side length c. It is 3 times the secant of 75 degrees, or 3 over cosine of 75 degrees, both totally fine. We still need to find our side length b. Okay, now I do now know the length of c, so if I set up something like the sine of 75 degrees, I would have opposite b over hypotenuse c, which I now know the length of. But let's go ahead and use our nice value of 3 as one of our given sides, just so that the numbers don't look quite as ugly. Okay, so if I want to use b and 3, I'm looking at the two legs, so I want to use either tangent or cotangent. So suppose I took the tangent of 75 degrees. That will be opposite over adjacent. Opposite 75 degrees is b, and adjacent is 3. So if I cross multiply, we simply straightforward get that the side length b is 3 times the tangent of 75 degrees. Now, I just want to point out, if you are using a calculator to approximate these things, make sure you know the difference between being in degrees mode and radians mode. If you are asked to approximate to 2 decimal points, if you're in radians mode and you put in 75 radians is a very different angle than 75 degrees, and you'll end up off. So make sure you know how to use your own technology. Anyway, moving on. Just like the last problems, we have a right triangle, we are given some information, and we are asked to find others. However, in this case, observe that the information we're given is 2 side lengths and no angles, except for the 90-degree angle, of course. Well, if I have two side lengths in a right triangle, I can use the Pythagorean theorem to get the missing one. Okay, so 1 squared plus b squared should equal c squared, which was 4. So 1 plus b squared is equal to 16, b squared is equal to 15, b is plus or minus root 15, but since it's a side length, I want root 15. Okay, so I'm going to take that information, I'll put it over here so I don't erase it later, and I will also label my triangle with it. So we found our missing side length straight away, but we don't know any angles, except for the right angle, of course. Well, let's go ahead and set up some trigonometric ratios involving the angles we don't know. For example, the cosine of angle B. Well, that's going to be adjacent over hypotenuse. Adjacent to angle B was 1, and the hypotenuse was of length root 15. So the cosine of B is 1 over root 15, which means B is the arc cosine of 1 over root 15. Again, if leaving radicals in the denominator is somehow seen as a problem, this would be the same thing as the arc cosine of root 15 over 15. And once again, if you're using a calculator to get an approximation here, make sure you know whether you're in degrees mode or radians. Okay, arc cosine produces angles either in quadrants 1 or 2, so this will be somewhere in between 0 and 180 degrees, so it will definitely be the angle that we're after. Remember, in the unit circle, you can have angles whose cosine is 1 over root 15 that are not in quadrants 1 or 2. Arc cosine only gives you the one in quadrant 1 or 2, but since we're dealing with actual triangles, everything is going to happen in quadrant 1 anyway. Okay, our other missing side is A, so let's go ahead. Our other missing angle, is capital A. So I could do something like, let's set up the sine of capital A. Well, that's opposite over hypotenuse. Observe that the opposite side from angle A is lowercase a, which is also 1, and the hypotenuse is still root 15. Which means that A is the arc sine of root 15 over 15, or 1 over root 15. And again, arc sine produces angles either in quadrants 4 or 1, and since we're in a triangle, the quadrant 1 solution will be the one we were after. We're not looking at anything in quadrants 2 or 3 when we're dealing with actual right triangles. So there is everything that we needed to find. Okay, if you don't know either of the two angles you start with, other than the right angle, of course, you're probably going to need some inverse trigs in here. Also observe, once we had B, we could have said the following. Okay, so I'm going to erase what we did to find A, because we can find it another way. As soon as you know one of the missing angles, in this case capital B is the arc cosine of root 15 over 15, we know that capital A plus capital B plus 90 degrees must equal 180 degrees. In other words, A plus B must equal 90 degrees, or A is 90 degrees minus B, which would therefore be 90 degrees minus the arc cosine of root 15 over 15. This is also correct, as long as you specify that your arc cosine function is in degrees, not radians. If you were in radians, you would simply want to convert everything to radians and call this pi over 2 minus the arc cosine of root 15 over 15. By default, most calculators, computer programs, etc. will work in radians, so be careful about that. All right, next problem. We've got a little diagram, and we are asked, let's go ahead and find the height of the tower. So observe that we do have a right triangle where this base was given as 70. We can assume that the tower actually goes up and it's not the leaning tower of Pisa at a strange angle. And we're given that this angle is 84.194 degrees. That's very specific. And what we're after is the missing height. So in terms of this angle, 89.194, the angle on the left, our unknowns are the height, our unknown is the height, and we know that this base length is 70. So what trigonometric ratio of that angle involves the missing height and the known 70? Tangent or possibly cotangent. So the tangent of 89.194 degrees is going to be equal to the opposite side length over the adjacent side length. The opposite side length is h, the missing height, and the adjacent side is 70. Multiplying both sides by 70 gives me that the height of the tower is 70 times the tangent of 89.194 degrees. And again, you would punch that into a calculator to get an approximate answer if you wanted. This is your first introduction to something called surveying. You may see people wearing helmets and reflective vests, carrying around equipment at the side of the road, pointing it at buildings and measuring angles and such, and they're basically doing this. By measuring the angles to various things from known reference points, you can estimate how long certain distances are, how tall buildings are, all of which is used to compute things like what's the size of a plot of land, because that area would affect its tax rate, etc. Okay, moving on. The angle of elevation of the sun is 36.8 degrees. At the instant, the shadow cast by an obelisk is 797 feet long. So what that tells us is, I've got an obelisk, and again, I'm going to assume that it is straight up. Okay. I do not know the height, but I do know that a shadow of length 797 feet is cast when the angle to the sun is exactly 36.8 degrees. Very similar to the last problem, I've got an angle, I've got an unknown height, I've got the length of a shadow which is known. So what trigonometric ratio of this corner angle will involve the unknown height and the known shadow length 797? That's right, tangent or cotangent. The tangent of 36.8 degrees is the opposite length over the adjacent length. The opposite is our unknown h. The adjacent is the known shadow 797 feet, from which I get that my height is 797 times the tangent of 36.8 degrees. You could punch that into a calculator to get an approximate answer. Just remember to be in degrees mode. Okay. 4-part problem. One of the tallest buildings in a country is topped by a high antenna. Great, so I'm going to start off by making a little diagram. We've got a building with an antenna. Okay. The angle of elevation from the position of a surveyor, so the surveyor is standing here on the ground, to the top of the building is 34 degrees. The distance to the top of the building is 2595 feet, and the distance to the top of the antenna is 2735. So notice there's a difference between going to the top of the building to the top of the antenna. The distance to the top of the antenna is 2735. The distance to the top of the building is 2595. And the angle to the top of the building, which is just this angle here, is 34 degrees. Okay. So we have several unknowns. We want to know how far away from the base of the building is the surveyor located. That's this. So extracting the information that's useful there, we see that this triangle to the top of the building has a hypotenuse of 2595 and an angle of 34 degrees, and this is our unknown x. Which trigonometric ratio of 34 degrees will involve those two? Either cosine or secant. So let's use cosine. This is going to be the adjacent side over the hypotenuse. The adjacent side is x, the hypotenuse was 2595. Multiplying by 2595 gives me x is 2595 times the cosine of 34 degrees. So there is our answer to part A. 2595 times the cosine of 34 degrees. How tall is the building? Well, not much changes compared to part A, except I'm not interested in the base of this triangle. If I'm interested in finding the height of the building, I am interested in this h right here. So now the relevant trigonometric angle is not cosine, it's sine. The sine of 34 degrees is opposite over hypotenuse. The opposite side is our missing height. The hypotenuse is still 2595, and multiplication by 2595 gives us h is 2595 times the sine of 34 degrees. So that's how tall the building is. Again, you can punch this into a calculator to get an approximation, but I'm more interested in the math rather than the computation. Okay. Now we move on to some questions that have to do with the antenna, so I'm going to erase my diagram that just had to do with the building. All right. What is the angle of elevation from the surveyor to the top of the antenna? So the diagram that's relevant there is this. I know that the distance to the top of the antenna is 2735. This is the angle that we're interested in finding out. I know the building goes straight up. You'll always assume that unless you're told otherwise. I don't know the height of the antenna, so I really don't know what goes here, but I do know how far away I was from the base of the building. This was x, as labeled in that diagram, which is 2,595 times the cosine of 34 degrees. Okay, so which trigonometric angle of theta involves these two items? It's cosine. Cosine of theta is adjacent over hypotenuse. The adjacent side length is 2595 times the cosine of 34 degrees. The hypotenuse was 2,735, which means theta is the arc cosine of 2,595 times the cosine of 34 degrees divided by 2,735. And you could punch this into a calculator to get an approximation, but this is a nice exact answer for a mathematician. Arc cos of 2595 times the cosine of 34 degrees over 2,735. Now what I do want to caution is that this arc cosine cannot be used to cancel out this cosine. If this was just the arc cosine of the cosine of 34 degrees, yeah, that's 34 degrees. But this cosine is being multiplied and divided by certain numbers, so the arc cosine is kept away from it. There's no immediate simplification to be done here. This is just what it is. And finally, what is the height of the antenna? So, to find the height of the antenna, we need to essentially do two steps. The first is going to be, can we find the height of the building plus the antenna? And then I can subtract the height of the building to get the height of the antenna. So the height of the antenna plus building, I'll call, let's just call it y, is this height here. Okay. There are a few ways we could do this. Because I know two sides of this triangle, I could use the Pythagorean Theorem. Alternately, because we have found the angle theta, I could use this angle theta, arc cosine of that big mess, and use other trigonometric ratios. But honestly, I'm actually just going to work through the Pythagorean Theorem. So x squared plus y squared is equal to 2735 squared. X was known to be 2,595 times the cosine of 34 degrees. So y is the square root of 2,735 squared minus 2,595 squared cos squared of 34 degrees. And that is the height of the antenna plus the building. So if this is the antenna plus the building, the antenna is y minus the building. So that is going to be this enormous square root minus the height of the building, which we found in part B. That was 2,595 times the sine of 34 degrees. So there is the height of the antenna. That's a nice exact answer based on the information we were given. It is the square root of 2,735 squared minus 2,595 squared times the cosine squared of 34 degrees minus 2,595 sine of 34 degrees. That's the answer to part D. If a calculator approximation is called for, you could punch that in and get a result. Okay, it's worth reiterating that I really don't like using a calculator to get approximations unless it's absolutely called for. Here is a nice exact answer. While an engineering firm would be a little upset with you if you gave that to them as a measurement, a mathematician prefers this to a decimal approximation 9 times out of 10.